Hi, everyone. Welcome to today's Geofabrics Academy, titled Resilient Strategies for Landslides Reinstatement and Mitigation. My name is Eric, and I'm the Technical BDM for Slopes and Walls for Geofabrics Australia. This webinar is recorded, so it will be available in approximately a week's time. So next week, just in case you're asking. And then there will be a Q&A sessions at the end. So please put your questions on the Q&A, not on the chat box. Depending on the time, we'll try to answer them after the end of the presentations. So let's kickstart. Now, it's a big topic, so I try to break it down into today's agenda under definition, causes, types of landslides, soil slope stability, and essential aspects for analysis, then the reinstatement measures and mitigation measures. Now, given the time limitation of 1 hour, it's impossible for us to cover. As I mentioned, this is a big topic, every single aspect. So the dominant part of the presentation will probably more on reinstatement measures, and the mitigation measures, probably a bit of a overview and the types of systems that the Geofabrics offer. There can be another, and there have been other presentations on, particularly on the mitigation measures in other presentations, okay? So just for your information. So the definition of and causes of landslide. The definition goes under the movement of a mass of rock or debris or earth down a slope. And the common causes of the landslides are such as rainfall, which is common sense, earthquakes, toe scouring, and human activities. Most of the time, these are the combination of factors that causes a landslide type of a situation. I'm not going to read through all of them. You can have a look at the later stage. These are the two most common landslides and will be the focus of the presentation today. And they are the rotational or circular slips that typically occur on a soil or weathered rocks type of slopes and tends to be deep-seated. And obviously the focus is what to do after the landslide has occurred, i.e. the reinstatement. Translational slips are typically soil or weak rock slopes overlying a stronger strata. They are relatively shallower or planar, and they also may be a creeping type of situation over a long time, but it can accelerate after a heavy rainfall or earthquake. These are the two types of special landslide types, and it probably forms more of a mitigation strategies rather than reinstatement strategies. And they are wedge or discrete rockfall type of issue, landslides. And wedge failure usually controlled by rock joints or discontinuities, typically do not creep, so the failures can be very sudden. The discrete rock falls are falling rocks from fractured rock slope face, and there are measures on how to contain them. And these form mitigation strategies. Debris flow or mudslides is even more special in this particular case. Normally in the valley of a hill slides, loose type of eroded debris at bottom of valley becomes saturated after a heavy rainfall, and they can travel a long way with very high velocity and large volume. Okay. Coming to soil slope stability and essential aspect for analysis, these are the main factors for stability of a slope. And it comes down to the angle of the slope. Obviously, the steeper the slope, the less stable it is. The ingress of water into the slope saturates the soil, creates pore water pressure, and it creates instability, obviously, in the process. And the natural soil shear strength of the material itself. And of course, the other factors, external loads like earthquakes or surcharge, okay, in a nutshell. And if you look at it in another form, these are the conditions and forms the basis for the reinstatement and mitigation strategies. Before we start to identify or the types of strategies, these are the essential properties we need to be collecting or aware of. So they are the geometry and soil strengths, i.e. the height of the slopes, downslope angles, top slope angles, long-term effective soil strength, loading conditions like live load, dead loads, earthquake, groundwater. And then the last one, performance criteria. I think this governs the entire scheme of reinstatement, and then how elaborate the scheme or the solution would be. And it is governed by certain territorial code type of guidance, such as councils or roading authorities or certain design codes requirement in terms of factor of safety. And they can be the static load conditions, seismic, groundwater, importance level, temporary or permanent. In a simplistic form, what a slope stability comes down to, you have a driving force, i.e. a shearing stress along a potential failure plane. And then you have the existing shear strength of the soil resisting that shearing stress from occurring. So the factor of safety effectively is basically the available shear strength over the shear stress of the failure plane. How to increase the resisting forces? Obviously, there are a few factors I mentioned earlier on. You can improve the drainage, either internal or external, or elimination of weak strata in certain cases, buttressing with retaining structures. And this is the focus of the presentation here today. Provision of in situ reinforcements such as soil nail or rock anchors, and improving the shear strength of soil such as stone columns type of heavy machineries type of constructions. And then these are the few parameters that are very important from a stability analysis point of view, and they are the ground model or the strata, effective cohesion for the long-term stability analysis, friction angle, density of soil, earthquake peak ground accelerations, and groundwater profile. And each of that items, I have nominate certainty and less certain, more certain, based on my experience, based on my discussion with the geo professions. You may have a slight different opinion on that, which is fine. But in a nutshell, what we are saying here is there is a lot of uncertainties to deal with at this stage. But they are the most important before we can proceed with a reinstatement or mitigation scheme, nonetheless, okay? But I mentioned here, for some small scale slope, most often back analysis of the existing slope profile before failure and mimicking the profile of the failure slip profile may be sufficient without going through the elaborative type of product, this investigation. However, when the scale and complexity of the slope becomes bigger, larger, the site visits, geological mapping, investigation, ground investigations are usually necessary. And this is where the experienced geoprofessionals like geotechnical engineers and engineering geologists are required to interpret and determine the above parameters and ground model. Some level of judgment is inevitable, and the key factors comes down to how extensive and how quality of the available data, quantity of the data, and how complex the geology is of the particular project size. One good source of practical guidance, can be found from this New Zealand Geotechnical Society, Slope Stability Guidance Unit 1, Part 4 and 5, published quite recently, October 2024. Once we've got the ground profile and we assign the ground profile into sections like this, into the most critical slip profile, and then assign groundwater if there is any, and the soil parameters onto the software program, computer program. This is a fairly straightforward type of profile. And then we can design structures depending on the width that you would wish to retain. In this particular case, a reinforced soil type of structures onto the soil profile. We're now coming into the reinstatement measures portion. So the definition of reinstatement is the act of restoring something back to its original form or better. Yeah. In the slope context, supporting road, we are talking about a failure that occurs either downslope, most of the time downslope, that affects a portion of the roads being, taken away. So we are putting the road back. And at the same time, there may be a widening opportunity in the process of reinstatement or reconstruction. So that's the context of the whole reinstatement measures here in this particular webinar. Now, when it comes to reinstatement measures, there are plenty, yeah. But as I mentioned, it's impossible to cover everything in this 1 hour or slightly more, I'm afraid today, due to the slides, yeah. So the red color wording or sentences are the one that we will be focusing on today, but we are not discounting the rest of the other measures, such as potential for modifying the slope geometry, i.e., making the slope gentle by cutting or filling or benching, okay? Then the focus, as I mentioned earlier on, is the buttressing or reconstruction with retaining structures. And they can be mass gravity, they can be reinforced soil, and they can be cantilevered pile, sheet pile, board pile, stone column, etc., which obviously is not covered today. In situ reinforcements are like before the slope fails or after the failure of the slope profile, recontouring the surface of the slope. And in addition to that, soil nailing to improve the stability of the existing slope, or in the rock slope condition, rock anchors or bioengineering using some form of a facing element that Geofabrics supply. And then erosion protection or preserving the stability. I think this is a given that every single slip reinstatement works is a necessity for all approaches. Irregardless of what you do, you've got to think of erosion protection anyway. And we don't have much time to talk about this vegetation and erosion control mat, but it's something that Geofabrics has plenty of option on, okay, in terms of product options. Drainage, likewise, we have the internal drainage products and lining of a swale drain products, but we don't have time to talk about it. But these two are a must, basically, in terms of forming the strategies for reinstatement of slip or landslide. And most of the time, as the scale of the job becomes bigger, you should think of a combination of the above, okay, to get the most optimum type of reinstatement measures. Last option, obviously, if you can think of it, is a retreat or avoid in terms of rerouting or diversion of the traffic of the road. Okay, I mentioned earlier on, there are many different type of measures. So we are going to zoom in and look at these type of structures mainly, i.e. the mass gravity, the reinforced soil wall, and reinforced slope. The rest, yeah, as I said, not discounting, but not going to be discussed here today. It is worth noting that there is no one-size-fits-all type of solutions. The solutions very much influenced and dictated by factors such as availability in that particular locations, skills of the workers, machineries available, budget, temporary or permanent, maintenance consideration, geology, importance of structures, scale, and performance requirement, among others. Okay. So case study number one is a straightforward mass gravity gabion of up to 5 meter high in Victoria, Melbourne area, whereby it involves some temporary shoring here while doing the excavation due to the importance of this particular road to maintain traffics. And the concern on the downslope, therefore, the design on the piles to support the load of the mass gravity structures for global stability. And this is how it looks like after the completion of the mass gravity gabion. Case study number two is has not been constructed, but a recent tender stage project whereby a slope, the slope is creeping, showing signs of distress at the top of the road here with some tension cracks and settlement issues over time. Now, the original proposal was to install, due to existing traffic and due to the concern on over excavation of certain type of retaining structures, this type of posts and what you call cantilever type of retaining wall was proposed with embedded pole type of a wall system. The alternative to that, and possibly a cheaper consideration to that, is a mass gravity veneers on the slope, surcharging, imposing a normal load or normal weight on top of the slope surface, preventing the creeping slope from occurring as an alternative. And you can see the improvement of slope factor of safety from before a 1.246 to an improvement of 2.36 with the gabion veneer. The third case study is also a Vic Roads project where the original proposal was to remediate or reinstate this particular slip failure with 750mm diameter board piles somewhere along the toe or somewhere along, yeah, I mean, the slip zone. And it was found that due to availability of machineries, due to limitation of space, due to the necessity to allow traffic to go on during the constructions, the board pile solution was deemed not feasible. And the solution or alternative is to use a mass gravity precast modular block called VertiBlock to be constructed at the selected founding location up to 3 meter high. And VertiBlock was selected due to the speed of installations of within 60 to 80 meters square a day. So that is the most important consideration of why this blockwork system, big size blockwork system, is selected for this particular project. So by the way, this is VertiBlock, 1.2 meter by 0.6 meter high and 0.9 into the soil with big hollow core to be filled with drainage aggregate, so free draining. And they are manufactured from 40 MPa compressive strength concrete. Yeah. They can be constructed most of the time up to 3 meter high without any soil reinforcement, i.e. geogrid. Otherwise, for taller structures, you can always incorporate geogrid to construct a taller structures. So before we talk about some case history on slip repair, let's talk a little bit on reinforced soil structures. So if you break down a reinforced soil structures, they come down to the components of soil reinforcement element, i.e. the geogrid, okay? And then the face element where the geogrid is connected to or in association with, and then the soil and internal drainage. The whole idea is when a soil is subject to load or under the self-weight, they tend to fail at certain slip plane, and in this particular case, plane AA, or a Rankine slip plane of 45 degree plus friction angle over 2. Okay, that's the slip plane typically. The incorporation of a reinforcement reinforce the block, forcing the slip plane to be intercepted by layers of reinforcement. Thereby, the sigma 3, which is the confinement stress, is negligible or not necessary and is taken care of by, in this case, the facing. So that's a quick summary or concept of reinforced soil. There are many technical attributes or technical benefits of why reinforced soil, such as a high resistance to dynamic loadings, in this case, earthquakes, more tolerable to bearing capacity, and etc. But one of the most direct and benefits is the cost of the reinforced soil structures. They are usually by far the cheapest, especially when the structures become taller. Most of the time, 3 to 4 meters taller, you would probably be looking at a reinforced soil type of structures compared to gravity type of retaining structures or cast in situ reinforced concrete, for example. And this is a study done in the 80s by Kerner, in 90s, sorry, by Robert Kerner, on the different types of costs of retaining wall versus the height. And the geosynthetic walls is always come down to be the most cost effective. So this is a typical reinstatement scheme of a downslope slip, okay, whereby you have a road on the top, you have a typical slip like this, and then you have done some soil investigation. You have identified that there are 2 types of soil. This is a weaker type, alluvial soil. This could be potentially a more competent type of soil, or it can, I'm just giving an example, okay? And there is the proposed scheme is to put up a steeper reinforced soil structures, in this particular case, 4.8. So what do you do in terms of the checks? You probably want to check, of course, from a reinforced soil design point of view, the internal stability of the block so that they are self-stable under the 12 kPa surcharge loading. And then compound stability deals with anything in within the block and externally, and global stability. In this particular case, a slip, potential slip that is involved beyond the block that you're putting in, okay, and involving the downslope, which most of the time you have to face, unfortunately, in a slip repair scheme. So, and this particular failure mechanism, global stability, all the time will be governing the cost and the final solutions that you're putting up. Yeah, so it is worth talking a little bit more on this particular failure mechanism. To do that, you probably want to, in the case of slip reinforcement versus a new structures that you're constructing from a ground, there are more considerations. And those considerations comes down to these few long-term type of a stability analysis, the groundwater, the earthquake, drainage, if there is a need of temporary protection, foundations and embedment consideration, etc. We'll discuss that a little bit later after this. Okay, now straight away, embedment is something straight from the British standard as a a code of practice. They actually recommend the embedment to be either h over 20, i.e. the total height divided by 20, or depending on the downhill slope angle, this dm, the minimum embedment depth, also increase in terms of requirement as the slope becomes steeper. Okay, so I'll leave you with that. Now I put out these boxes here in terms of the things to remember, things to consider to meet the short and long-term stability with the adequate factor of safety. It needs to consider, obviously, in terms of the internal zone and external face. This is the facing system of the reinforced soil, or in the case of mass gravity, no facing system. And this comes down to above ground retaining structures design, either the mass gravity or reinforced soil, according to the respective local regulations or code. Okay, in Australia, for example, AS 4678, and etc. The external or top part is probably something to more on the prevention and precautionary measures, i.e. to more on a drainage consideration, prevent water from entering or ingress, or prevent surface runoff from eroding the upper portion of the retaining structures. Now, the bottom part, external foundation or back, either nails, anchors, or horizontal drains, soil replacement, consolidation, piles, stone columns are optional items depending on the soil conditions. And this is the part that usually quite costly, okay? Depending on global stability requirement. It governs whether or not these few items are necessary, okay? And we'll discuss a little bit after this. Now, when it comes to design of reinforced soil structures, again, just a bit of a quick one slide to talk about internal stability. In short, it comes down to the determination of the layout of the geogrid reinforcement and spacings, in other words, and length, okay, layout, that they are strong enough so that they do not rupture under the cell weight or surcharge loading, external loading. And the second part is they are long enough to prevent the pull out of the geogrid or the soil wedge due to the slippage of the shearing of the soil. The third part comes down to the checks on the failure through the connection between the geogrid and the types of facings. Certain types of facings are more critical on connection strength compared to the other type of facings and how vertical you are constructing your reinforced soil structures. This can be another presentations, but I'm just going to leave that for now with this internal stability. External stability is not much different to conventional retaining wall design in that the entire reinforced soil block is viewed as a composite material, composite block, and you are checking against the sliding on the base of the entire block, overturning and bearing tilt failure and slip, in this case, global stability. Okay. Seismic. Seismic is obviously a very important consideration for the design of this type of structures, especially so in New Zealand, okay, not so much so in Australia. For that, we need to know peak ground acceleration, okay, PGA, in the respective zone for that structure located. most of the common design methods use pseudostatic, i.e. the earthquake shaking is modeled as an additional static loading. Now, because of that, there are some limitations because the equation, the formula breakdown after you exceed certain G, okay? And that limitation comes down to, in AASHTO, they mention around and about 0.29 G, okay? And however, the NCMA says, considers okay to use this pseudostatic method of up to around 0.4 G. Otherwise, anything exceeding this 0.4 G, the pseudostatic method will become over-conservative. Yeah, the result becomes not that reliable. Yeah, you likely ended up with very long reinforcement. Yeah, due to that limitation in the formula. And then in Appendix I of the AS, it says seismic performance of polymer geogrid structures in a number of strong earthquakes shown they have excellent seismic resistance. Yeah. Based on experience and past earthquakes on the reinforced soil structures, the seismic design should be okay with minor shaking using the standard static design factor of safety. Minor shaking may be possibly somewhere around 0.1 to 0.15 G. The moderate shaking, the geogrid layout from the static is usually adequate, but maybe slightly longer. And that is where the 0.15 to 0.2 G that comes in. Strong earthquake is where more than 0.2 G, both the length and geogrid may likely be determined by the seismic load cases. When it comes to reinforced soil structures for seismic design, there are two mechanisms for seismic that we need to be aware of. The first mechanism is what we say, the mechanism that do not cut the soil reinforcement. So because of that, and due to the nature, the ductile nature of the reinforced soil structures, in other words, they can tolerate movements without failure, okay? Some form of some level of deformation on the face is tolerable. You can and therefore attenuated. The forces can be attenuated. You can reduce the peak ground acceleration by around 50%. So the horizontal acceleration in this case becomes 0.5 of the peak ground acceleration. But for any mechanisms that cut reinforcement, such as the wedges, two-part wedge or single wedge in within the zone of the reinforced soil, or partly in reinforced soil, partly out of reinforced soil, you cannot allow deformation to occur. Yeah, otherwise the reinforcement is going to rupture. So some form of amplification of the peak ground acceleration is suggested, and that goes by that particular equation there, given by both AASHTO and NCMA. Now comes down to, I mentioned earlier on, the very important factor of safety for global stability, most of the time governing whether additional measures like foundation improvement or the soil nails behind the reinforced soil structures is required. They are not a fixed number. However, most Australia and New Zealand geoprofessionals use 1.5 factor of safety for static load case, okay? And seismic load case, a lower factor of safety may be used. And in this particular case, AASHTO permits 75% of the static load factor of safety for seismic case, and Federal Highway allow factor of safety of 1.3 static case and 1.1 for seismic. I mentioned earlier, since the ANZ industry uses 1.5 for static, and therefore their seismic becomes 1.125 in most cases. Okay. However, I wanted to show an example of Hong Kong geotechnical manual for slopes in terms of their approach, in terms of the recommended factor of safety, depending on two factors. And they are the economic and life risk factor. Why Hong Kong? Because this is the geo guide or geo manual that prior to me migrating to New Zealand, what I've been referring to a lot while I was in Malaysia. And this is the summary table in terms of the life risk and economic risk. And there is one particular criteria condition. There is a 10-year return period rainfall. So you probably want to know that rainfall period intensity. Once you know that, and you can apply to use this table for most of the slope design factor of safety. And you can see there from a factor of safety of more than 1, obviously has to be more than 1, to 1.2 and 1 up to a 1.4 factor of safety. So very recently, probably 1.5 years ago, the Auckland Council in New Zealand also published this code of practice for land development and subdivision under Chapter 2, Earthworks and Geotechnical. They also have varying factor of safety, global factor of safety, for different type of conditions under normal water, groundwater, worst credible groundwater. You see here, pseudostatic seismic loading under ULS PGA for varying factor of safety and under different application. Obviously, with a building platform, you have a building sitting on the top, the factor of safety becomes very important, 1.5, the structure, sorry. Service and maintenance access area, slightly less, 1.4 in this case, and amenity area, 1.2, etc. Okay. So all I'm saying is it's not a fixed number and it affects cost considerably. So this is a discussions the geoprofessional probably likely to have with the client in this particular case. So other territory authority or crown entities may have their own performance criteria. So it's important for you to refer to that respective code. So before we move on to some case studies, I wanted to show this very nice, in my opinion, brilliant graph showing the difference of factor of safety, okay, and annual probability of failure of a slope under the different class or category of design or so-called quality in this case. So obviously the category 1 are the best design in terms of soil investigation, quality of the data, quality of workmanship, you know, the best basically. And it is very clear now from my earlier slides about uncertainty, about quality, you know, about availability of data. Even though if you design for a factor of safety of 1.5 versus a factor of safety of 1.3, but following this different category in terms of the quality, you will get different probability of failure. In this particular case, a 1.3 factor of safety is having slightly lesser, 1 to the power of 10 minus 4 versus 1 to the power of 10 minus 2, even though the factor of safety of 1.5. And this is a source that I've obtained from the New Zealand Geotechnical Society, Slope Stability Guidance Unit 1. It's a good source of reference, basically. Okay, now we're going to show some case studies that has been constructed. Some of them, we, Geofabrics, got involved directly in the very early stage of feasibility stage of helping and assisting the engineers. technically. Some of them some level of input, but we supply system and products. So this particular one, which we have involved a very early stage, is the Eureka Bend, Takaka Hill. About 11.4 meter high slip. As you can see, it involved about 110 meter long of slip areas. And the initial concept of reinstatement options comes down to filling up the entire slope area, including the downhill, with a bulk of filling, very costly and slow, or otherwise build a bridge across, okay? And the third option was a reinforced soil structures, plus some soil nailing behind the excavation profile during constructions to allow for the traffic to go on. So this is the challenge, main challenge, basically, to maintain the single lane road during constructions. So this is what I mean. Excavation, first stage, lay the surface with temporary nail, by the way. This nail is ignored in the long term. So non-galvanized. So to ensure the single lane, excavate down up to the intended founding level, okay? And then build a reinforced soil structures, in this particular case with a green terra mesh unit with rock fill front face, layers by layers, up to the final finish level. 12 years on, this was taken in 2020. I visited the site, and not a single sign of cracks on the road surface after the completion. And this is the case studies that has been reported in the New Zealand Geomechanic News June 2010 issue. Case study number 2 is Ray Hill in Kawakawa Bay. As a result of intense rainfall in August 2008, about 400 cubes of surface slip occur, blocking the 2 lanes coastal roads, to the Kawakawa Bay community. Okay, the slip was very quickly cleared and removed by the maintenance contractor. However, it was discovered during the clearing from the contractors that a major landslide have been identified with the development of tension cracks observed, enveloping the entire house platform at the top. And this is the house platform that we're talking about here. Okay, so we're talking a major landslide issue rather than a surface slip for this particular case. And further investigation from the engineer have discovered that they have plotted that this is the tension cracks discovered, and some direction of the landslide have been identified, and it is very clear that this particular slip is just a smaller slips compared to the much bigger one. And it is very much concerned that the 5 properties downslope here would be inundated by the next event of a rainfall. Therefore, emergency actions has been in place within the council and the engineers to evacuate the properties, and some reinstatement or stabilization schemes have been conducted. So the scheme comes down to removal of about 65,000 cubes of hill slope at the upper portion, and further excavation of the loose material at the toe, and replaced with around about 25 meter high of 100 meter long reinforced soil slope, 45 degree, okay, layers of reinforcement. Then horizontal drainage, lots of horizontal drainage into the hillside due to high groundwater table and discovered. And further to that, due to the height of the slope with a shorter reinforcement length, the engineer has designed and further to the reinforced soil block, a very long ground anchors to improve the global stability to a satisfactory level of 1.5 in this particular case. So this is the photograph showing the construction ongoing of a 25 meters high structures, earthworks of recontouring of the slope with hydroseeding and vegetation establishing. And this last slide here showing vegetation established on the 45-degree reinforced soil slope, 25-meter high. And again, this is a case studies, if you're interested, reported in the New Zealand Geomechanics News, June 2010. The case number 3 is a segmental block facing after the failure in Turnbull Bay, Portobello Road in Dunedin, of around 7 to 8 meter high, 200 meter long. And this is how it looks like after the completion with the use of TW3 block incorporating a positive connection for seismic resistance. Case number 4 is a rather small slip, 4 meters high, with a gabion terramesh structures constructed in 1988 using the terramesh panel as reinforcement and rockfill gabion face, a Great Ocean Road. But I think the highlight for this is the completion after 23 years, photos taken, and 30 years after completion, there is no single sign of corrosion in the very aggressive and severe atmospheric exposure environment for Great Ocean Road using the double twist mesh gabion with the proper coating, obviously. Case number 5 is again a slip involving a scouring of the toe due to the rising of the water, river water, in winter months especially. So the highlight for this is basically the use of a combination of different facing type. The lower portion using gabion due to water concern, and the upper portion using a green terramesh unit with vegetation over top to minimize the cost of importation of rocks and expedite the installation speed without stacking the rock at the top. Case number 6 is when you have more or less competent ground material, but surface slips. And when the space is tight where, there is only one lane road, you may consider using only the gabion as a thick veneer, as a skin or veneer, with some veiler beams for the ground anchors to retain the surface material. Trapezoidal shaped structure is quite often when you are dealing with slips or landslide, you may encounter portion of it or part of it is competent ground, and whereby you do not need to excavate further to lay the soil reinforcement. You may consider using what we in the code of practice consider trapezoidal shape, where the code allows you to have 40% instead of 70% usually, and gradually increase the length of the reinforcement up to 70% at the top. Or subsequently, if this condition does not exist in i.e. competent ground, you may create that competent ground, to allow for a trapezoidal shape structures to be constructed due to not having to excavate too much for the risk of live traffic, say, for example, one condition. And then in the Federal Highway guidance for this type of MAC structures, they allow for this type of very slender type of, so only 1.5 meters length minimum, okay, when you have a very stable rock, but having the top 1 meter, 3 foot of minimum 0.8 of the total height, sitting on a very firm ground. I have to say, I haven't come across this a lot. We haven't done this either, but I thought I'd put it up here. But one thing to note, not for urban roadways widening due to greater risk of tension cracks, typically suitable for low volume road only. So very low traffic, forestry road, those type of condition that you may consider this type of technology or approach. Lastly, before we move on to mitigation, for low traffic volume road again, under FHWA, they have this method called deep patch, whereby they utilize several layers of soil reinforcement to slow the development and propagation of roadway displacement over some creeping slopes, i.e., you have found some tension cracks on the road face, and chances are that this slope underneath has been creeping over time, and the roading contractors have been, piling up a silt layer and piling up materials over the years, and it keeps settling and settling. This may be one method to slow down the creeping condition, but yeah, bearing in mind that it's not a complete solution, but to slow it down until further funding or further when the road becomes a more important type of scenario. Okay, so this is one of the method mentioned in FHWA. Okay, coming to the mitigation section. Now, mitigation is reducing the risk of loss from the occurrence of any undesirable event. And again, in the slope context, we can divide that into preservation of the existing stability of the slope and enhancing the stability of the slope from a certain factor of safety of 1 to, say, a factor of safety of 1.5, things like that. And this is what we call control at source. Or when the problems most often time becomes slightly bigger, complex, then we can consider what we call passive protection structure. And this is control away from the source or threat area. And again, it can be a combination of the above. Let's have a look very quickly what it means. Preserving existing stability for rock slopes, it basically comes down to applying a drape of mesh. There can be different type of mesh subject to design, subject to slope height, and etc. The design often comes down to anchor loading requirement, crest rope diameter, anchor spacings, and the mesh type for the given rock slopes. And the anticipated and how active the rock, discrete rock fall is going to occur. So this is the term we use, simple drapery mesh. Okay, this particular project and photographs here shows 2 weeks after the mesh has been applied over a very undulated, active rock slopes. You see how active these rocks. Loose rocks are, well, that's the whole purpose of applying a mesh there. We don't have time to go into much detail of the design of this. It can be for another sessions if you are interested, or let me know. Then the other part of using the mesh for rock slope comes is what we call anchored mesh or secured drapery, where the anchors stabilize or improve the stability of the rock slope by intercepting some kind of a discontinuities. And then any loose material in within that is contained by the mesh. Yeah. So this is where anchored drapery, by using the different type of mesh, and it's part of the design to contain the loose rock within the 4 anchor points. Okay, so that's the second at source control options. Then for soil slopes, we use more or less similar type of mesh. Again, different mesh for different type of slope condition, but they usually comes with, in addition to mesh, for stiffness and for density against within the nail head for soil nail, an erosion control element. Okay, and we use MAT-R for that. And soil nail, again, like rock anchor, is the stabilizing element. Plates and mesh is responsible for holding the surface slope material intact while the vegetation takes place, and usually catered for slopes up to around and about 60 degrees. Okay, we're moving on to passive protection structures. So I think the question is, when do we use passive protection structures? And I mentioned earlier on, it is usually used and considered when the problem becomes larger. And it is very clear from here that from these two approach, the simple drip and anchored drip, as you have the height of the slope becomes taller and taller, the cost is proportionate to the height of the slope. If you can design a passive protection structure intercepting the falling rock at the right location, then the cost of inception stays the same, okay, irregardless of the height of the slope. So the main whole idea and whole objective of a passive protection structures comes down to they are installed at the right appropriate location, okay, identified under the trajectory analysis, protect away from source the threat of rockfall or debris flow, and therefore the structures are there to be designed to receive the impact energy of a rockfall or dynamic pressure of a debris flow. They are usually scaled, I mentioned earlier on, when the scale becomes greater and complex, and quite often can be combined with at source control to optimize the design. So the first type of passive protection structures comes down to what we call the ETA, or EAD, sorry, or formerly known as ETEC 27, certified rockfall fences. And they are certified nowadays from 35 kilojoule low energy barriers all the way up to 9,000 kilojoule with their rating system independently certified under the EAD procedures. These are the systems that works through deformation to attenuate and to dissipate the very high impact kinetic energy of the falling rock. And these are some of the project photographs that has been installed in mostly New Zealand. That has been some of them has been proven in terms of their ability to arrest multiple rock impacts. This one here, the 2,000 kilojoule impacted by a number of about 600-700 meter diameter rocks. The next type of passive protection structures is what is known by a mineral or green terra mesh reinforced soil bund. They can be constructed to be designed for up to very high absorbing energy, up to 10,000 kilojoule can be designed for. And again, the reason for reinforced soil structures or bund is the high ability to absorb energy due to the ductile behavior. And you can see from here performance of multiple rockfall behind this 3-meter high bund, and also a shallow landslide or debris flow arrested behind the bund. So again, these are some of the photographs, cases that has been installed successfully and used and proven for this 1.2 meter diameter rock in Kaikoura in New Zealand. The last type of passive protection structures is a debris flow fences. So instead of rock fall, these type of fences either channelized like this, okay, to be constructed in within the channel, yeah, or open slope with posts, yeah, are designed to arrest debris flow, okay. After severe rainfall, usually the loose material will collected in within the valleys, and this is where usually the debris flow fences can be installed. They're usually custom designed depending on impact velocity of the debris flow and volume of debris flow, or some kind of imposed pressure to be designed for. Lastly, this is Ohau Point. It is a very famous location along the Kaikoura Coast Road, and it's just showing you the scale and severity of the landslide after the Kaikoura earthquake, and some of the measures that has been carried out on this one particular location. You can see at source control, scaling, sluicing, benching, rockfall fences, avoidance, constructing using sea walls. Yeah, multiple type of approaches or measures has been used this particular case. Yeah, and lastly, a 600-meter long rockfall fence constructed at the toe to mitigate the residual risk for this particular location. Okay, how am I doing in terms of time? Sorry. Okay, apologies for that. So thank you very much. And oh, 4 minutes over time. So sorry about that. As I said, there's quite a bit of slides and topics to cover. If you have any questions, this is my contact details. I'll have a look very quickly whether there's any questions in the Q&A sessions. Okay. How long, first question from Fred, how long did the case study 3 solution take to construct? And second option, how often do you clear the back of mineral green terrace mud for maintenance? Okay. Question. Case study 3. Let's have a look at what the case study is. Okay. This particular case study number 3. Okay, this is case study number 3. 200-meter long. Look, it's been quite some time. I forgot how long it takes. Quite often, the time of slip repair not just comes down to the construction of the retaining structures itself, but foundation preparation and discovering any surprise geology, quite often, sometimes something like that. But what I can tell you is for this type of system, the segmental block wall system, particularly the TW3 with the mechanical connector, they usually take one construction team, i.e. 3 person plus a compacting machineries and plus a digger, okay? So one-man crew, about 25 to 35 square meter a day, okay? I hope that gives a bit of an idea of how quick this type of production. There's another presentation that I did some time ago on phasing options for reinforced soil structures, whereby I talk about the different installation rate of the different phasing systems. Okay, this is a moderate one. The quicker one, as I showed earlier on, is the verti-block, bigger size blocker type of a wall system, if speed is your concern. Second question comes down to this particular clearing of the rock. I think it depends on under a maintenance schedule for passive protection structures, we want something that with the height. So as soon as there are some debris collected at the back of the passive protection structures, it makes sense to clear them quite immediately. And for your information, there is a manual called Maintenance Guidance of Passive Protection Structures published by the Waka Kotahi, the NZTA of New Zealand. Okay, talking about some recommendation and guidance for maintenance and including the clearing frequency. I hope that gives you a bit of an idea. Okay, so I hope, okay, that's it. Okay, I hope that gives a bit of a good appreciation of a fairly quick introduction and review of a landslide reinstatement and mitigation measures. As I mentioned, if there's any further questions, please feel free to contact us. Thank you very much for your time.